All right, thanks, Alicia, and welcome everyone. We're delighted to have Peter Zoller here. Peter probably doesn't really need an introduction in the JQI, but nonetheless, I'll do it anyway. So Peter has had contributions everywhere in atomic physics, condensed matter physics, quantum physics. It's actually, I was looking back at some of the seminal things, and it's really kind of amazing. So really the first paper to suggest optical lattices and neutral atoms for quantum simulation was a paper with Peter and his student, Peter Jacques. Ion traps for quantum computation comes about from the famous Zoller paper. And now Peter even has a quantum computing company called Alpine Quantum Technology. I'll plug your company for you. Quantum networking, DLCZ protocol, very famous. The Z in that is Zoller. Rydberg atoms for quantum computation. That one actually kind of got started when he visited us at NIST in around 1999, I guess. And Peter literally wrote the book on quantum noise. So there's a very wonderful textbook called Quantum Noise with Peter and Crispin Gardner. So I could just keep going on and on. Peter's, of course, won practically every prize, almost every prize one can win. Maybe a few left to be won, Wolf Prize, National Academy, et cetera, et cetera. So I'm not going to keep going. I'm going to let Peter go ahead and talk. So I'm happy to have Peter tell us about tomography and quantum simulation. Peter.
Okay, so let me thank you for the invitation to speak at the JQI seminar. I see many friends here, via my Zoom link. Of course, a person-to-person contact would be a little bit, better, but I think it's actually quite amazing, that these seminars over the internet actually work so well. So let me also say that I remember these good times that I had actually at JQI, like these ideas about the Rydberg blockade that we came up together when, for example, Steve Rolston and I talked about Rydberg excitations of atoms that had actually quite some impact also now when we see all of these tweeze arrays and so on. So there's a lot of connections that I guess that I have with JQI. What I would like to speak about here today, I called it in the announcement, Entanglement Hamiltonian Tomography in Quantum Simulation. And I added the word up here, efficient, and that means actually scalable, because this is really what we would like to do here. And my talk here has very much to do with the attempt to completely characterize and also measure, to come up with measurement protocols that are applicable in a very broad range of today's quantum simulators. So let me give you a little bit of background and all of these things. First of all, I want to mention the people involved in this work. I mean, the first 4 ones, they are co-author of the paper that I'm mainly talking about, and the last 2 ones, well, we are just now in the phase where we are trying to write a second paper that goes in quite a different direction. Maybe I have one slide at the very end to say a few words about that. You're not the people I have to show this slide over here. I know the world of quantum simulators and platforms from, I don't know, cold atoms, tweeze arrays, and so on. And this is Marcus Geiner's experiment, or the trapped ions that we have here in Innsbruck, but also JQI and so on. I think it's very clear that from an experimental point of view, we have now, great toolboxes like single site quantum control and measurements. And I think the general question to be asked is how do we measure now complex many-body observables beyond the usual? By usual, I mean that, well, think of a quantum gas microscope. You can measure certain kind of correlations, but can we measure things like, say, Rayleigh entropies and all of these things that are maybe nonlinear functions, or maybe even the von Neumann entropy that I will show you what then actually later during the talk. So I should maybe explain a little bit about this, why I'm interested in this topic, and actually this interest in the topic of how to measure entanglement, the entanglement spectrum or the entanglement Hamiltonian. It sort of started about the time when Mohammed and I started talking about these things, and we actually wrote this paper together. It's called Measurement Protocol for the Entanglement Spectrum of Cold Atoms. And Hannes Bichler did this work when he just arrived, actually, this was at Harvard, leaving Innsbruck. And Mohammed had some ideas along these lines, and all of these things were put together in this protocol over here. And it's kind of interesting to read now. It says here, entanglement, and in particular, the entanglement spectrum plays a major role in characterizing many-body quantum systems. While there has been a search of theoretical works on the subject, yeah, that's true, no experimental measurement has been performed to date because of the lack of an implementable measurement scheme. Wrote this in 2016, and actually the protocol that we came up with there is not something that has made it to the lab today, but in a somewhat different way. We somehow continued working on this. And when I talk today about this entanglement Hamiltonian tomography, it is the way of not only measuring the entanglement spectrum or the entanglement Hamiltonian tomography, it very much also has to do with the fact that we were able to analyze some of these data that were hanging around from Rainer Blatt's group in a completely different context. This was Rayleigh entropy measurement, that we can now, using a new kind of protocol, reinterpret or interpret as an efficient tomographic protocol where we can actually measure entanglement spectra, for example, in quench dynamics. And this is done here, 20 ions, subsystem of 7. It's a pretty big system, and I hope that I can convince you during my talk here today that these ideas that we talk about are actually, for me, kind of really open up almost like a new era where we can study, quantum simulation and doing measurements on a level that was somehow unprecedented. But I guess that we should really start out by giving a very general, and I apologize, even almost a tutorial introduction into what an entanglement spectrum is and what an entanglement Hamiltonian is. I like this sentence that Marcello Dal Monte, when he was with us, actually wrote in one of our papers. It says, the entanglement spectrum and the entanglement Hamiltonian play a paradigmatic role at the interface of entanglement theory and many-body physics. This sounds very pompous, but I think it's actually true. And I would like to give you 2 examples. The first one, sort of what really got me into the whole story, which was the Lee-Haldane conjecture. The second one having to do with quench dynamics. That's the experiment that we were sort of analyzing with our theory. And I want to take them as kind of introductory examples for what I'm doing in the following. So what's the role of entanglement in many-body physics? Well, let's think of a lattice. I'm just drawing here a few lattice. They might have some Hamiltonian in the background. And what we want to study here is the bipartition of this lattice into a region A and a region B over here. And for simplicity, let's assume now, being interested in closed systems, that we are describing, say, the ground state or maybe quench dynamics, whatever it is, by a pure state wave function psi. And of course, there would be a decomposition of the Hamiltonian into an HA, the first part, HB, the second part, and HB connecting the first and the second part. It is this HAB that's, of course, responsible for creating entanglement in our quantum many-body states. And the quantity of interest that we'll be interested in the following is the reduced density matrix, where you trace out the system B and you would like to know about the system A over here. So if I trace B, I get what's called the reduced density matrix. And there's a way of rewriting this reduced density matrix that I have here, a density matrix living on the Hilbert space of my subsystem. And I can always diagonalize it. The eigen values, I would call them e to the minus psi. This is a convention up here. You call this thing here the entanglement spectrum. And of course, if you want, you can also, decompose this or just rewrite this density matrix here as e to the minus h tilde a, and we call this thing over here the entanglement Hamiltonian. So the entanglement Hamiltonian is nothing else but just the logarithm of this rho a that we have over here. And to make this thing a little bit clearer, let me connect it also to what we call the Schmidt decomposition. In the Schmidt decomposition, you take your state vector that you have up there, the state vector psi, and you decompose it into a part of the left and the right. And you can see that the Schmidt decomposition goes in a sum from alpha equal to 1 to up to some value chi. And then it is a superposition over here, weighted by this e to the minus psi. That's my entanglement spectrum, or we call this coefficients here also the so-called Schmidt values. And you can see right away, if chi is equal to 1, this thing will factorize. It is a product state. But in the cases of interest, when you have entanglement, and if you have a lot of entanglement, then this chi that we have over here will be very large. And what we are after is really that we would like to characterize an entangled state, basically asking, can we measure this Schmidt decomposition that we have over here in quantum simulation? maybe for ground states, maybe for quench dynamics, you know, just name it. I mean, any states that you want in this context. And can we learn something about quantum phases in this context?
Peter?
Yeah?
Yeah, this is Bill.
Yeah.
Is chi greater than 1 both a necessary and sufficient condition for the system to be entangled, or simply a necessary condition?
Well, if something is a product state, you know, then it is not entangled. Then everything which is not a product state is entangled. So chi larger than 1 that you have over here would correspond to an entangled state.
Well, I guess what I'm wondering is that it seems, well, I'm just trying to think and having a hard time thinking about that sometimes it's not always easy when I look at a state written out that way for me to immediately tell whether it's able to be written as factored or not. And
there's a very simple way of finding out, to answer your question. So, I mean, if you give me a wave function psi over here, I can calculate the reduced density matrix. And suppose that I make a spectral decomposition. I just solve, you know, the eigenvalue problem, somehow making this matrix row A here diagonal. These vectors that appear down here in the Schmidt decomposition, they are just the corresponding eigenvectors. And so this chi that appears here is the rank of the density matrix. And if the rank is equal to 1, then the density matrix is just a simple projector. This means that chi is 1. There's just, you know, one state over here, this a simple projector, then it would be a product state. But if the rank is larger than 1, you know, there's many eigenvectors. So it's not one eigenvalue 1 and the other ones are all 0. But there's many eigenvalues over here. We'll see that afterwards. Then you would call this thing entangled.
Yeah.
So simply eigenvalue the reduced density matrix and look at the rank, and this will be the answer.
Okay, well, let's go on.
Okay. Let me give you 2 examples. And I said the first one that actually brought me into this entanglement spectrum business on is the very interesting relation between entanglement spectrum and topology. There's something which is called the Lee-Haldane conjecture. The Lee-Haldane conjecture makes a very interesting statement about the entanglement spectrum. This is that you got a many-body system over here. Imagine that you got a spin system and you cut it into 2 pieces. And suppose that you look at the entanglement spectrum that I talked about now earlier. And on the other hand, you have a topological phase, and I will explain now in a second that this Haldane model, or this it's actually an AKLD model over here, will correspond to a topological phase. Then we have edge states. You have edge states over here. We got an edge state over here. And it turns out that the entanglement spectrum, by cutting a system in the bulk apart, and the spectrum, the physical spectrum that you had for the edge states over here, turns out to be identical. And that's a very deep relation in topology. Every paper today that you read on topological phases will analyze the entanglement spectrum. And let me just explain very briefly what the idea is. This is what got me into this whole business. And the model here actually is the following one. It's called the AKLD model. Look for the ground state. And this model looks at the spin 1 chain over here. Yeah, spin 1 chain. If you got a spin 1 particle, I can always write it, you know, as a triplet state, which is coupled from 2 spin 1/2s. So if I have 2 spin 1/2 and I couple them, I got a singlet and a triplet. Imagine that the singlet state is somehow punished so much in energy that only the triplet remains. And then it turns out that the ground state that you got in this whole AKLD model is a topological phase. And the way of seeing that is that these you know, artificial spins that you introduce, the spin 1/2, they form a singlet across the boundary here. You can see that they form a singlet here, here, and here. You can see that the edge states are sort of these lonely spins that are left over on the left and the right-hand side. These are the edge states. They are spin 1/2, even though we look at the spin 1 chain over here. And if I cut now this system apart into 2 pieces, you can see that there's a singlet connecting them. And this singlet connecting them is essentially just this entanglement across the boundary. And if you work out what the corresponding entanglement spectrum is in this model, well, you can write it, of course, as a matrix product state. You find that the bond dimension is 2. It's just a singlet that you're cutting in this place over here. You find that the signature of topology is that the entanglement spectrum has 2 degenerate states. And there's a 1-to-1 correspondence with the boundary space. So this is this famous, you know, spectrum of edge excitations. It's the same as the entanglement spectrum. You can also do this thing for a Heisenberg chain and still see that. I mean, there's a gap over here, and you can see the degeneracies over here. These are the signatures of topology. You can see them in the entanglement spectrum. And of course, the seminal paper that was written by Haldane, and I think it was 2008, where it says that the low-lying entanglement spectrum can be used as a fingerprint to identify topological order. He talked about quantum Hall, actually fractional quantum Hall, where again, you get these edge excitations over here, where the edge excitations that you have in the system is the same as the entanglement spectrum. Nobody has ever measured these things. We are not going to measure this thing in the talk now today, but I think what we have now is that we are getting ready, gearing up for developing tools where in our artificial or synthetic quantum method that we're doing in quantum simulators, we might be able to detect these things. So we are trying to develop tools along these lines. That's one of the goals. And this has helped for me being the driving force.
Peter,
But let me now switch over.
Go back to the Heisenberg, the previous slide with the Heisenberg spectrum of the Heisenberg model.
Yeah, this one here.
Yes. So I would have, if I'd been asked about that, I'd say those two are sort of trivial degenerate ground states, but there's something more to it than that, is there?
Well, the point is that the degeneracies over here, okay, for example, that you see in this AKLD model, I mean, the fact that you got a lot of other states up here simply means that the Heisenberg model is a lot more entanglement. It is this degeneracies down here, which is this fingerprint that we can see for these topological edge states over here. You can see that there's a spin 1/2 and there's a spin 1/2, and there's a one-to-one correspondence between these edge states and the degeneracies that we find in the entanglement spectrum. So signatures of topology have to do with finding degeneracies in the ground state of this entanglement spectrum, and this allows you to do sort of the counting of all of the corresponding states. Yeah.
Okay, because I mean, I guess I would have, if asked to give a quick answer, I'd say, well, the degeneracy in the Heisenberg model just comes from time reversal invariance or something like that.
Well,
S goes to minus S.
This is the Heisenberg spin 1 chain, and it is a topological phase. And this thing down here, this different sectors, they are the fingerprints to sort of quote now Haldane. Of this topology, and this goes actually very deep. I mean, there's this paper he does the Reed Moore state and all of that, and I'd like to see these things measured in an atomic simulator. But as I said, let's change topic a little bit and let's talk about quench dynamics, and let's talk, I mean, very soon now about an experiment, with a trapped ion simulator where we can try to measure some of these things. So second topic is entanglement spectrum and quench dynamics. And here, the whole thing is conceptually, of course, much simpler than what I said earlier. Imagine that you do an experiment, you got a string of, say, ions over here, could also be Rydberg tweezers and so on. And we look at time evolution here, having some quench dynamics. Take your favorite Hamiltonian here, I'll write them down afterwards. And then what you can ask is this, that, well, suppose that initially we prepare a product state over here, and will evolve over time. After some time, the state will be entangled, possibly even very highly entangled. And so we can ask ourselves, what's the Schmidt decomposition that we have that sort of builds up during this time evolution over here when the initial product state involves in quench dynamics to something that becomes a very highly entangled state. So again, we can pick now out a certain subregion here, define our reduced density operator, and also the corresponding entanglement Hamiltonian. I said before that what we really are after is this: can we monitor, for example, how this Schmidt decomposition over here, and this really means that we would like to measure the Schmidt values over here, how this grows from an initial product state to a highly entangled state. This will teach us a lot about thermalization of the system. So all of these dynamics of building up entanglement in quench dynamics, this is encoded into the measurement of this entanglement spectrum over here. And so you can see that, the question, can be measured this in quench dynamics? And of course, you can always do it by just doing a kind of a tomography for this thing over here, but tomography is very expensive. So we would like to do these measurements, something that's efficiently scales actually in an efficient way with the system size. We would like to do systems that eventually are much, much bigger than what you can do in tomography. This is the physics question that we want to ask. And let me just sort of, as a side remark at this point, make the following statement. most of us, when you see this reduced density matrix, and then you take the logarithm and you call this thing the entanglement Hamiltonian, but it looks like a Gibbs ensemble over here, of course. They have very little intuition, but let me remind you that if I would go in the quench dynamic for a very long time and my system is thermalizing, I don't have any somehow conservation laws in here, we sort of know, at least this is what your teacher taught you, when you went to a class in somehow quantum statistical mechanics, that this at the end becomes a Gibbs ensemble. And actually in this case, you know what the entanglement Hamiltonian is, because for the Gibbs ensemble, it's simply the total Hamiltonian of your system projected, on this little environment A that we have over here, this subregion A. So in this case, we sort of know the entanglement Hamiltonian is a physical Hamiltonian. And I just want you to make one observation over here. We will afterwards talk a lot about the operator structure of this entanglement Hamiltonian. This is one example where you can see that this entanglement Hamiltonian that we talk about here in thermal equilibrium is actually just the physical Hamiltonian in the region A. And all of us know that physical Hamiltonians, they are local, quasi-local. I mean, they just have two-body interactions, three-body interactions or whatever, but they're very, very simple operators. So your rho A may be very complicated, but your H, your Hamiltonian or your entanglement Hamiltonian over here might have a much, much simpler structure. So when we talk about trying to get the hand on rho A, it may be much, much better to think about the entanglement Hamiltonian and the corresponding operator structure. And this local operator structure will actually now be a key observation in the following. And it's much more general than what we talk about here. And we'll see afterwards a short discussion of the Bisognano-Wichmann and conformal field theory, where some of these things are sort of proven within serious mathematics. And for us, they provide then partly a motivation, something that we can test and so on. So this is entanglement spectrum in dynamics. And well, all of you have seen this picture of these beautiful labs that I got here from Rainer Blatt, of course, with the IQOQI simulator. In the meantime, they have now 50 ions under control in this simulator. The first experiments are now slowly, I guess, coming along. And all of you, I guess, also know that we have here realized an Ising model with a transverse field over here, which is long range in these models. I mean, at JQI, I don't have to explain these things. And, in our context, this was written in part of these papers that are down here. And of course, there's always been kind of parallel papers at actually JQI. I mean, also talking about ion trap quantum simulator in the way that we do in a very similar way here. So many of these things that I talk about in the following apply immediately to the ion labs at JQI. Let me now sort of right away go to connecting what we do and show you that we can actually see this thing in an experiment. I'm not going to tell you how we actually calculated this thing by comparing theory with experiment. At the moment, I just want to focus on what the essential physics is in quench dynamics that I would like to sort of read out from the plots that I'm showing over here. So here we talk about an entanglement spectrum in quench dynamics, and we talk about an ion experiment at the end. Let's take 10 ions. We can use very similar things with 10 and we take a subpartition of 1 to 5. So here's my ion trap simulator. You can see it over here, the ions evolving in quench dynamics from initially product state to something which in the end becomes a pretty highly entangled state. And we would like to look at the subsystem 1 to 5 that we can see over here. This is the region where we would like to have the reduced density matrix. And of course, what you can do as a theorist is that, well, typically these experiments are done in this limit where this effective magnetic field is much larger than J. This is just a flip-flop Hamiltonian, but long range. That makes it slightly more interesting. And what happens now is this. This is the plot of the entanglement spectrum. You can see here lambda, my Schmidt value, e to the minus psi alpha. I'm starting out over here with a product state. And the product state simply means that the lambda over here, is equal to 1. This is my product state. And all of the other lambdas, I got a density matrix, which is in the subspace of 5 qubits. So it's 2 to the power 5. So there's only one eigenvector that has eigenvalue 1, and all of the other ones are actually 0. This is the indication for the product state. And while you involve, this is theory over here, you can see this the black line that goes down here. You can see all of these other eigenvalues coming in. This is the buildup of entanglement during the quench dynamics over here. And I've already indicated over here that we can not only do the theory, we can also simulate this entanglement Hamiltonian tomography protocol that I will explain then afterwards, we can simulate on our theoretical data. And you can see that there's this orange little band over here. If I assume that I do at the end with randomized measurements, 500 random measurements and then 150 normal measurements in the system, typically what experimentalists do, you can see that our protocol that I will explain later on is able to reproduce that over here. From this, we're able to extract things like the von Neumann entropy that grows over here, okay? But this is just theory, so why do you care? Well, this is sort of what we want to do, this build-up of entanglement of the Schmidt decomposition from the product state to the very highly entangled state. Now we can take our techniques, and I just show you the results for the moment and explain how we get that afterwards. These are experimental data here. You can see that at the very beginning, the experimentalists don't really prepare. This is not really a pure state. It should be one over here and the other one down here. This is a little bit imperfections and decoherence. But you can see that if you go down here, all of these data points, they lie just exactly on where they're supposed to be. So I find that this is not only the first measurement of the entanglement spectrum on this scale over here, extracted from experimental data taken in a completely different context. This was the science paper from last year with Rainer Blatt and Christian Roos. But we have here the first measurement of the entanglement spectrum. And as I said earlier, we can do that also for example, 20 ions, and we got very similar agreement here. What's kind of interesting in this context is, well, we see here the buildup of entanglement kind of life. You can see the Schmidt decomposition, how it evolves and how it grows. But knowing now that Hamiltonian, and I'll come back to these things a little bit later, knowing the Hamiltonian, we can compute on our classical computer, once I know the Hamiltonian, sort of the experimental quantities like the von Neumann entropy. And you can see here, the black line was this theory. If I have uncorrected data, not accounting for any proper decoherence, I just take my raw data. This is what Rainer Blatt would advise me to do, this red curve over here. It sort of follows. And if you correct with our models that we have, that we can test, you can see that we can, I guess this is the first measurement that you can see of a von Neumann entropy extracted from experimental simulation data with these trapped ions. And if you want to see more details about this, this is sort of the evolving here, the entanglement spectrum. It's here was the e to the minus xi. This is just the entanglement spectrum directly. These very large values up here, they're a little bit inaccurate, but they just have to do with the fact that if I take a large value here, it makes a very small contribution to the entanglement spectrum. There's sort of a perfect agreement here in the entanglement spectrum in the build-up of while the system evolves from a product state to a highly entangled state. And of course, we cannot go to the limit where these things thermalize, because at the very end, there may be some other forms of decoherence coming in, and we have to start modeling decoherence. And I will not enter that, the modeling of decoherence right now here on the present level of the discussion that I'm doing now here. So this was sort of a second kind of a teaser, why the entanglement spectrum is interesting. It shows you on the way to thermalization how entangled states are building up, and we are able to measure that. I'm leaving a lot of sort of open ends over here. Let me make a short list of topics that I would like to discuss, because I will tell you now in a little bit more detail now what we actually do and how we do this entanglement Hamiltonian tomography to make it in particular efficient, that allows us experimentally to go, in this case here, to subsystem sizes of 7 out of 20 ions. And I'm sure that we can do much, much larger systems based on scaling arguments that I will present later on. I think the best way to talk in particular to experimentalists is usually to just give them kind of, I would call it a recipe. Usually they're willing to look at recipes. What do I have to do? And then once you see that the recipe somehow makes sense, then you will ask the question, why do we want to actually do that? And what's actually behind it. So the entanglement Hamiltonian recipe that we are doing actually is the following one. We're going to make an ansatz for our reduced density matrix by assuming at this point, but we will test it afterwards, that this entanglement Hamiltonian actually has a very, very simple structure. I gave you one example earlier. It was the thermal state, where this thing would simply be some Gibbs ensemble, for example. But my statement over here is this: let's assume now for the moment that this HA has a very simple structure. So this HA depends on very, very few parameters. I will show you examples now in a minute. And then the protocol, sort of to say it in one sentence, is that number one, you fit to an ansatz of experimental data. Number two, we can verify that if this ansatz works or not, and we can improve the ansatz. And this gives sort of a loop where we can either then say, well, we succeed, and we found a very simple Hamiltonian here, and if this works, it is extremely efficient. So we only need very few parameters and therefore very few measurements to do that. But sometimes there may be definitely cases where this simple structure of this entanglement Hamiltonian is simply not true, and our protocol will also find out. Okay, that's kind of what the basic idea is. At this point, you might say, well, what's actually the physics behind this local few body ansatz? And the physics behind it, well, there's some very deep things in certain cases like Bisognano-Wichmann Conformal Field Theory, and I will comment then on them a little bit later. And even then, that this kind of an Hamiltonian tomography that we do here provides a new kind of a testing ground for Bisognano-Wichmann and conformal field theory. And so this is opening kind of a new frontier, I would say, in quantum simulation, where we start to test conformal field theories based on their predictions, you know, with these kind of techniques that we talk about here. I will illustrate this by examples. And at the end, we're doing tomography over here, even though in an efficient way. I will talk about a little bit about quantum algorithms. So let me elaborate on what I said on one slide, now going through these things in a little bit more detail and sort of pointing out in a slower way what the underlying ideas are. Normally when you say, well, what we have to do in our business is simply that we want to measure a reduced density matrix, and your first reaction will be, well, in many cases, at least with spins, for example, we can simply do quantum state tomography, and that's of course true. Well, you would simply measure this thing on your quantum machine that you have. You might diagonalize it, getting the entanglement spectrum, and you wouldn't really see a reason why you should take the logarithm of all of that at the end, but I'll comment on that later. But clearly there's a problem, and the problem is that this thing doesn't scale. All of us know that doing tomography is very expensive. You know, it always scales exponentially, and if you do Hubbard models, it doesn't even exist in this case. But the point that I would like to emphasize here is this: this tomography over here becomes efficient at the point where you can make a statement that you know something about the quantum state. In quantum information, you want to be completely agnostic. You would like to be blind, you know, what your quantum state is. Maybe you don't want to make any assumptions. In our context, the statement is we are doing quantum simulation. So in our case, all of the quantum states that we're analyzing are derived from a Hamiltonian. And these Hamiltonian, actually the physical ones that we have in the lab, they are local, quasi-local Hamiltonians. They have a very simple structure. So does this quantum state that we have over here actually somehow know that the origin behind it was a very simple Hamiltonian that was local, only contained few body terms? Well, and that's exactly behind what I tried to explain earlier, that this fact that the reduced density matrix has stayed over here came originally in quantum simulation from many-body physics, where we have only local interactions. The end, in many cases, not at all, translates into the fact that this entanglement Hamiltonian actually has a very simple operator structure. It is by itself just a local Hamiltonian, and as a matter of fact, even more simple. If you take your standard Hamiltonian that you have, you know, that when you write it over here for your Hamiltonian, if you make a deformation of this Hamiltonian and just write this same Hamiltonian with slightly different coefficients, over here, it turns out that this is a very good fit for the entanglement Hamiltonian. So what I'm saying over here is this, that we have some physics inside that we are putting in now as an ansatz. And now, of course, what we want to do is that the protocol will go like this, that we make an ansatz over here with open parameters. There will be very few because it's a polynomially small Hamiltonian that we are writing here, very few terms. We can fit to data. We can fit to data with very few measurements. And then second, and this is very important, it's not only that we can fit, because if I fit, I always get an answer. Do I believe the answer? We can verify that what we have over here actually works. And this verification is sort of based on what we called in a series of papers cross-platform fidelity verification. So we can verify that what we get over here actually is really true. And once we get a certain fidelity threshold, we can do some classical post-processing, finding, for example, the entanglement spectrum. Or you might simplify, well, this is a bad fit, and then you go on and you add some additional terms, make the structure of this Hamiltonian more complicated. At this point, potentially discovering new physics, because there's physical meaning behind these terms that we have in the entanglement over here. And you would like to see the physics, which is encoded in this entanglement Hamiltonian, maybe then also be revealed in the measurements that we do. Well, this sounds sort of very abstract. So let me summarize this kind of measurement ideas, a little bit more directly. So what I just described you, what was done is behind the plot that I showed you before, but let me now illustrate it by more details. So step number one of our recipe simply means the following. You ask the experimentalist, what kind of Hamiltonian do they actually implement on their total system? I got here a system of ions, and I did, for example, a transverse Ising model over here, with having a field which is assumed to be large here. So we just have hopping terms over here. This is the Hamiltonian that an experimentalist might implement in the lab. So then the question is, what's your ansatz that you do when you go into all of that, in order to write down the ansatz for the entanglement Hamiltonian? The idea is simply just copy this line that you have up here down here again, but now constrained to the subregion A. But let me relabel the coefficients in the Hamiltonian Jij up here as J tilde, and use this J tilde here as variation parameters. This is the first ansatz, physically motivated, that you can make for the entanglement Hamiltonian. But there may be some deviations from that, and you might start adding certain terms. And I would like to show you now, if you analyze these experiments and you start to play this kind of a game, how within a very small set, of these zero-order Hamiltonians, very few variation parameters, we converge to be able to fit in an extremely good way the reduced density matrix in our quantum simulation Quench. And this is behind these results that I showed you earlier. So this was step number one. Let's make an ansatz, and the ansatz was very simple. You give me the system Hamiltonian, and I simply deform it. There's some deep insight what these these somehow deformed quantities are, but I'll come back to this thing later. So how do we do that? Well, step number two is this, that you would like to confront your ansatz with experimental data, okay? And how do you do that? Well, some of you may know that we have worked on what's called randomized measurements. So what you do there is this, that suppose that you take a string of ions, you produce your quantum states. We have studied measurement protocols where you apply random unitaries here, scrambling up your quantum states and getting probabilities. And all of these things then leads to sort of, depending on the random unitaries, random bit strings that your quantum simulator is spitting out. And from these randomized measurements in the past, we were able to extract a lot of quantities. Actually, we shared some interest together with Mohammed, like this, extracting from these randomized measurements here, topological invariance, or this more recent paper also, about many-body Chern numbers is based on these kind of ideas. But what we do in our context is that, well, we are applying these randomized measurements. And as I said, Rainer Blatt has some data lying around, taken in a completely different context. We fit our entanglement Hamiltonian to this data over here, getting a certain, fit parameters. Actually, it's very inexpensive to fit because the number of parameters turns out to be very small. And at that point, you can go to the second, and that's a very important step where you say that can we test and then maybe even improve the ansatz for the fidelity estimation. What you do is this, that you have a given data set and you split it into two parts. In the first part over here, you apply your procedure, but then you do a cross comparison. You want to compare the quantum state with the first with the second one. We wrote a paper how to do these things. This was came out at the beginning of this year, with Andreas Elben and Benoit Vermeersch as one of the key people behind it. That gives us, this fidelity over here when we compare the quantum state that we think we have, and you compare it with some new additional experimental data. So we do a quantum comparison of our reduced density matrix. And suppose that I take now the original Hamiltonian that I had here before, the one written over here, and then you do it during the Quench dynamics, and you do it here for 10 ions, and then do it here for 20 ions. You can see, well, actually the agreement is not so great, because for this Hamiltonian that we have over here, turns out well, all of the theorems like conformal field theory, they don't apply to these parameter regimes where the experimentalists were. But what we can do at that point is that we can start to add additional terms, few body terms. There may be some 3-body terms and so on to the Hamiltonian. And you can see if I just add a few terms, and there's still, we talk about a very small number of parameters over here, we get an essentially perfect fit, with the experimental data over the whole quench region that we have over here. This works for 20 as well as for the 10 ions. So at this point, probably your question will be, do I learn something from the additional data down here? I mean, what we do is at the moment purely heuristic. I mean, you just make ansatz, you have very few, and obviously you have your success. Do I learn something behind it? Let me now switch over and try to talk about sort of, the deep reasons behind some of that and how I see the techniques that we are doing over here actually somehow become, a test of some these kind of ideas, become a novel tool set to explore problems that are at the foundations of quantum many-body physics. And I want to talk now a little bit from the theory side, what kind of things these kind of ideas are opening, where you talk about tests or confirmation of the Bisognano-Wichmann ideas or of conformal field theory in the context of quantum simulators. I think there was a question.
Yeah. So maybe you're about to address this, but what I'm wondering is the extra terms that you would add in order to try to get a better fit. Are these unique, or what if you had chosen some different form for the extra terms? I mean, I guess this goes to the question of what do you learn? Are you just adding more parameters to get a good fit, or is there real physics behind the idea that you would choose this particular form?
Well, I would say at the example that we discuss over here, these are just in some sense unique in the sense of being minimal, best approximations to parameterize your density matrix. Your density matrix lives in the subspace of 2 to the power 5 or 2 to the power 7, has a huge number of complex numbers that you have in there. And the amazing thing is that we are able to summarize this complete density matrix, for this complete time that we have over here in quench dynamics in terms of these very few interaction terms over here. If you ask me at this point, give me a physical interpretation for these terms that we are adding over here, then I can only tell you, well, for this particular situation, I don't have it, but maybe it's time to start thinking about it. But I will show you now in the following discussion that we do have examples where we have a theoretical understanding of what some of these terms could be. And I will show you that, for example, that conformal field theory predicts certain terms, not in the particular context, because we are not in the domain of conformal field theory over here, where we are able to answer these things and we are able to see terms in this entanglement Hamiltonian that are predicted by conformal field theory that have actually a very deep physical meaning. At this point, just take it as being heuristic and a minimal description that somehow seems to work, and you might ask yourself, why does it work? Okay, and this why sort of is something that we are going to enter now in the following discussion when I talk about this Bisognano-Wichmann theorem. It's just one example illustrating that.
Yeah. Now, so one more point. Effectively, what you're doing here is you're saying, let me guess that my entanglement Hamiltonian is the physical Hamiltonian, because I know that if the system were...
No, it's not what I'm saying. It is a physical Hamiltonian, okay? It's not the physical Hamiltonian, because if it was the physical Hamiltonian, you would be in thermal equilibrium, but you are not.
Exactly.
Okay? So that's a very specific structure, and that's exactly the discussion over here I would like to illustrate now in the following with the Bisognano-Wichmann theorem. This will address, I guess, your point in a...
Well, right. The thing is that what you're doing is you're making an initial guess, which you don't expect to be correct, but you expect it to be close.
Yes, but okay, let me emphasize that what we do over here is actually really that when we are writing down here, for example, this system Hamiltonian, these J's over here and the physical Hamiltonian, they are known parameters. The experimentalists know what they are. These J tilde down here, they are variation parameters, and there's a certain spatial dependence, and I will talk about the spatial dependence and the meaning of that, what comes out over here. This is teaching us something about the entanglement structure of the Schmidt vectors that we have. So I'm entering exactly discussion in somewhat different context right now.
Right. So the physical Hamiltonian is basically giving you this first guess for the form of the Hamiltonian. You're going to fit the parameters of that, but then if it doesn't fit, then you're going to add some more terms.
I add some more terms, and eventually I know some cases where the conclusion definitely would be, the density matrix does not want to be fitted, by some local ansatz that we have over here. So, but if it cannot be fitted, we find out. So what I'm saying is, what we do is systematic, that we make an ansatz and we can improve it, but there's definitely the option that it can also fail. But I have a lot of arguments why in most or many physical cases, ideas like this will actually work. Okay, and it basically goes back to the fact that the physical Hamiltonians underlying all of these things are local Hamiltonians, the mother of all of these things. This Hamiltonian is quasi-local over here that we have. And somehow the quantum states that are generated in our many-body simulation, they somehow remember that. And this is at the end then encoded in the fact that these Hamiltonians over here have to zero order a very similar structure, but plus these additional terms over here. But at the level of my discussion right now in relation to the experimental quench dynamics, this is a purely heuristic thing that we can sort of test and see that it works at the end. But you will ask, of course, correctly, what do we learn from it? Well, what we learn at the moment is that we can measure this way the eigenvalue spectrum and see the Schmidt decomposition live. I mean, this was the discussion that we had over here, that we could really see how the entanglement builds up, this measurement of the time evolution of the entanglement spectrum, seeing how the system evolves from a product state to a highly entangled state, eventually even thermalizes over here. This is what we can see without maybe knowing in detail what the individual terms of the Hamiltonian mean here. Yeah. But as I said, in other cases, we know. And this is what I want to go over now.
Now, is there any sense in which the success of this depends upon the system evolving to something that's close to the equilibrium state, or is that not at all an issue?
Well, okay, I mentioned before, and I guess that's also what you're pointing out, and you're right. If I go on here forever and my system is here, doesn't have any integrals of motion, I would expect, this is what your physics professor taught you in quantum statistical mechanics, or maybe you taught it also to other people, that this should go over to a Gibbs ensemble. So in this sense, to some extent, we are actually testing that, over here. So in this case, the entanglement Hamiltonian and the physical Hamiltonian on the subset is the same. Actually, right. Conformal field theory will tell you that this is not entirely true, because it's not the original Hamiltonian. It has actually a cutoff, and we can actually test this cutoff. So we can test much more sophisticated predictions than the one that you would know from the Gibbs ensemble. The Gibbs ensemble is an approximation, again, in some sort of a thermodynamic limit where edge quantities are imprecisely represented. But you will see, I will not do that actually here in my talk, but we have examples where we can actually see that from our theoretical simulations with an experiment showing these things still to be done. So we can test very specific predictions of conformal field theory that give us some insight exactly about what you're talking about.
Okay, thanks.
Okay, but maybe we move on for the moment, because I think that some of these questions that you're asking will be answered maybe in a somewhat different context by this following discussion that goes now in a somewhat different directions, because I want to switch from quench dynamics now to ground states and give you a very simple illustration of something that we call here the Bisognano-Wichmann Theorem, in quantum field theory. This is a very, very deep thing in quantum field theory. I want to tell you what it is. Once you see the word theorem, you say it cannot be violated. Well, this theorem is derived under certain assumptions, and quite amazingly, when you apply these ideas to lattices, where this theorem is not a theorem, and to a lattice which is not the continuum quantum field theory, then it becomes an approximation. But amazingly, we will be able to see that we can make predictions about the structure of the entanglement Hamiltonian for ground states that are of the type that I told you earlier, and I would like to guide you now through the discussion doing that. So I have to say that for me, this whole thing started out, with quantum simulation spectroscopy, this paper with Marcello Dal Monte, who's in the meantime moved to Trieste. And so a lot of these insights that I'm going to present at the next few slides are really due to Marcello pointing it out to us, and then for us sort of further developing it. what is the Bisognano-Wichmann theorem? It comes in quantum field theory, and it is a statement about the ground state, which means the vacuum in the quantum field theory. So it is a very, very deep thing. It talks about entanglement in your vacuum state. Okay, that's what this thing is. And let me give you a very sort of a simplified version of all of this. It works in all dimensions, but let's talk about one dimension. Imagine that we have a one-dimensional system, which is infinite. It goes from minus infinity here to plus infinity. And if you are a quantum field theory person, you would write down a Hamiltonian, of course, as a local density h, this calligraphic h of x over here. This is the local theory. When we do quantum gases, we write down quantum field theories that are local or quasi-local. This is what I mean by this h over here. But suppose now that we take this system up here and we go to the ground state. At the end, this will be the ground state in our case of our many-body system, our spin model. And I do a pi partition into A goes to plus infinity and B goes to minus infinity, and I'm tracing out the B, and I'm just interested in the right-hand side over here. And then amazingly enough, Bisognano-Wichmann gives you an exact expression for this entanglement Hamiltonian. And it tells you the following. It tells you that the reduced density matrix on the right half space that goes from 0 up to then all the way to infinity has the form of a Gibbs ensemble, okay? But it's a very special Gibbs ensemble, Bill, and this is also what's related to you were asking. It is a Gibbs ensemble that has a local temperature. You can see normally in a Gibbs ensemble, you would say, this is just beta, your inverse temperature, but here beta is a function of x, of position. And at this point, let me appeal to your intuition. If I got an entangled state living over here, of course, if you look at the edge of the system over here, this is the one that really knows about the entanglement with the rest that we have on the left-hand side over here. And this entanglement.
Excuse me, Peter. We don't see your pointer anymore.
Don't see the pointer? Does it not see? Don't see that? Okay. Maybe then what I should do is, sorry, to go out here for the moment and sort of. Can you see that? Now it's back. Sorry.
Yep, it's back.
Okay, sorry for. Okay, so it simply means that the density matrix get more and more mixed, sort of, if you go to the edge, because there's more and more entanglement over here that sits at the edge. And this is represented in the fact that this local temperature, this Bisognano-Wichmann, the inverse temperature goes to 0. So this beta of x over here is proportional to x. So we have here like a local temperature Gibbs state. If I come closer and closer to the boundary over here, the higher my temperature is, my effective temperature, signaling me that I got more and more entanglement in my system. And there's a very definite prediction now here, because it just means that, this object over here simply means that give me your old Hamiltonian over here, your Hamiltonian density, multiply this thing by x. This is my coordinate, like a ramp. And this is the new entanglement Hamiltonian. So you can see that we get the entanglement Hamiltonian as a deformation of the original Hamiltonian if I just multiply my Hamiltonian over here with x. Okay, this is the statement, what this theory tells you. Okay, so we have a definite prediction, and you can see it's local. So when I talked before about local Hamiltonians, I mean, it wasn't sort of, out of the blue sky. It's really related to some very deep, reasoning in quantum field theory. Example here, the Bisognano-Wichmann for ground state. So, of course, if I take Bisognano-Wichmann, it's giving me an explicit expression for my Hamiltonian, simply telling me, take your original Hamiltonian and multiply all of the coefficients with a spatial ramp. And let me illustrate that now for lattice models. Suppose that I take a spin 1/2 Heisenberg chain like I did before, and I write down a Hamiltonian. What will it be? It will be a Hamiltonian. Well, we got XX, YY, and CC couplings over here. This is a Haldane chain, and it just has constant coefficients. All from minus infinity to plus infinity. All coefficients are the same. This is your physical Hamiltonian. Bisognano-Wichmann tells you, you want the entanglement Hamiltonian. I give it to you by simply writing the same Hamiltonian all over again, but now these J couplings that are over here in the right half space, of course, they are proportional to M. So I'm sort of constructing the decouplings while the move to the right gets stronger and stronger and stronger and stronger. So in this sense, I can say that my entanglement Hamiltonian is a deformation of the physical Hamiltonian that I had originally. This was the physical one over here, all coefficients constant, but now they're just like a ramp. They go up sort of linearly. It's quite an amazing statement, you know, it's very, very deep. And at that point, you might say, does it work? No, we can actually simply go and test these things numerically. And this is what was done in this original paper. This is the essentially the entanglement spectrum. And you can see here the solid line. You can see the dots over here in different topological phases and so on. To an amazing accuracy, this Bisognano-Wichmann Theorem, even if you put it on the lattice where it's not supposed to be true, describes, you know, all of these eigenvalues and so on in an amazing way. So the conclusion, the take-home message is that you took the original Hamiltonian, and Bisognano-Wichmann tells you the entanglement Hamiltonian is just the original one on the subregion, multiplied the coefficients by a ramp, just some linear x dependence. And if you do conformal field theory, take something from the center, then it would be some parabolic dependence. And the agreement numerically in these examples that you can test here is amazing. Well, actually, Bisognano-Wichmann comes with a small constraint, and this is the fact that you got Lorentz invariance over here. So we can construct examples where this thing also does not work. But I would say that in the majority of cases, this thing works. Okay, there was a question here.
Yeah, Peter Zoller, this is Garnet Bryant. Is there a reason why it should be linear instead of just any monotonic function that's increasing?
Well, as I said, for example, if I take here a situation where I go to a ring and I cut out a piece like the A that you have over here, it turns out that the corresponding function would be a parabola. Conformal field theory, you can do conformal field theory, do conformal mappings, and then the answer is, well, it's not linear. The linear simply comes from the fact that you have an infinite space and you cut it in half, and then it turns out to be linear. If you take out the subregion, it turns out to be a parabola. So any finite size region will typically have a deviation from the linear ramp. So if I at the end go to a quantum simulator and I don't take an infinite, quantum simulators don't tend to be infinite, I take a subregion out, which is actually finite, I will see deviations from the linear ramp in terms of some quadratic dependence and so on. And I will show you afterwards how this actually comes out from when we simulate simulations of our measurements and do the tomography. You can see exactly the kind of things that you are talking about. Okay.
Thank you.
Okay, so you can see that Bisognano-Wichmann gives us an analytical expression. It is a local Hamiltonian. It has this non-trivial ramp, and numerically these things fit even in a regime where you would expect. It's very surprising that these things actually work so well. You know, in this paper over here, what we did is that we simply said, we test the Bisognano-Wichmann theorem on lattice by our theoretical numeric simulations. And then what we said is, well, if I ask an experimentalist to deform the Hamiltonian according to this prescription, they can physically simulate this Bisognano-Wichmann Hamiltonian and do a normal spectroscopy and therefore get these things out. But you can see that with the tools that we have now available and what we're doing right now, we can actually do much more. We can ask the question, Bisognano-Wichmann tells us, you know, what the structure of this entanglement Hamiltonian is. And we can put this guess of Bisognano-Wichmann into our fit of experimental data. It is a local Hamiltonian, a deformation of your system Hamiltonian. And then we can say, what is the best fit of our entanglement Hamiltonian tomography? Does it then reproduce Bisognano-Wichmann or not? Okay, so we are developing here testing grounds. Therefore, some of these very deep theorems like Bisognano-Wichmann on the lattice, we can actually test, you know, to what extent these ideas that are very deep about entanglement theory in the many-body system, if they're true or not. And that's exactly what's sort of being opened on the fundamental frontier, I would say, by these kind of ideas that are pursuing here. Let me show you one example. Suppose that somebody had an ion trap simulator, but in this case, what actually prepare a ground state. I know preparing a ground state is not very easy. It has been done by Chris Monroe in Maryland, of course, in some non-perfect way, because you have to do adiabatic passage. Then what would this experiment actually give us? You know, we would know if I measure the entanglement that, well, my ansatz, according to Bisognano-Wichmann for the entanglement Hamiltonian, would have this form, and that the J tilde and the B tilde over here, these are my variational parameters if you want, they should have the form of a ramp. let's simulate this thing. We as theorists can simulate this experiment. You know, we can calculate the exact ground state. We can apply entanglement Hamiltonian tomography with this ansatz and simulate what would actually happen in an experiment and ask how many data, you know, how many measurements do I have to do all of these things. Let me show you the results. This is these beta coefficients that we have over here. Can you see the linear ramp over here? Bisognano-Wichmann comes out very, very accurately. You can also see some error bars over here. This is done for simulations, I think 22 lattice sites, but it turns out to be very few measurements. It was mentioned before, you said that why is it not parabolic? Well, if I have a small system size and for certain other parameters, there's a linear part, then it goes parabolic, okay? How well does my entanglement Hamiltonian actually reproduce the entanglement spectrum? Well, let's go with this model that I have over here over a quantum phase transition. If I take B very large, I have a paramagnetic phase. If I take B very small, I have a ferromagnetic or antiferromagnetic phase over here, okay? You can see that in the entanglement spectrum. Can you see the degeneracies over here? These are the degeneracies that indicate the entanglement spectrum dominated by this phase over here. And then we can see the splitting up. The black lines are the theoretical calculation. This is our tomography here. You can really see how across the quantum phase transition, we can monitor what happens to this entanglement spectrum over here. And we can even reproduce the eigenvalues, you know, down to the level of 10 to the minus 7 with our techniques. So extremely accurate, the entanglement spectrum here. The right upper plot here, you know, shows the efficiency that when we start increasing the system size, how many measurements does it take? This is the vertical axis here. If you do standard tomography, you can see this is the number of measurements it takes. It increases here exponentially with the system size. You know, if I do a rank 2 tomography, this is basically a rank 2 density matrix. It still goes up here. With our tomography, you are down here. So this is extremely efficient, where with just a few parameters, you're able to test something like Bisognano-Wichmann, you know, on your quantum simulator machine. That's sort of the link or the claim that developing these techniques where Bisognano-Wichmann motivates your ansatz, but at the end you can test it, you know, in a reliable way with the experiment. That's kind of what the idea is behind it. And let me sort of come now to the conclusion. I just have a few more slides now. That we can do similar things in a much more complicated context. Can we test conformal field theory? Conformal field theory gives you explicit expressions for the entanglement Hamiltonian in quench dynamics, how the system evolves from some initial state to finally a thermal state, and how things happen in between. There's some analytical predictions for these things, and we can now, and they all contain the fact that the entanglement Hamiltonian are actually quasi-local. But this temperature that I talked about before, that was position dependent, will now be position as well as time dependent. You know, this is one of the predictions, and there will be even more additional terms that we can test for all of these things. And I just want to show you one example, you know. So conformal field theory predicts corrections to the entanglement Hamiltonian. Can we see that? Well, there are certain additional terms that the conformal field theory tells you that should be visible in quench dynamics. And indeed, when we add these additional terms, this is without this term, this is with this term, these additional terms that we have to add to the deformation of your Hamiltonian, they now have physical meaning, and they have to do with entanglement flow in the system. And our technique very uniquely is able to identify these additional contributions to this entanglement Hamiltonian and how they appear as a function of time, you know, is able to identify these things, and therefore we are able to make a very deep connection to conformal field theory. We have a test of conformal field theory, but all of these things that I talk about is that we can apply, of course, these techniques also outside the immediate regime, where maybe conformal field theory is no longer valid and we have no theory at all. But we can still ask the question, is the entanglement Hamiltonian quasi-local, and have a systematic test for all of these kind of ideas. So I guess that these two examples, Bisognano-Wichmann and conformal field theory, sort of, and the deep foundations that we have in this context in quench dynamics for ground states, they sort of indicate that the kind of ideas that we are pursuing over here may be a very interesting new frontier in quantum simulation. And you can see here, if I leave out this term, you get this kink over here, the exact goes here. And if I start to include this term, we can explain everything in quench dynamics. So we can discover new physics in here. At this point, I'm at my summary and outlook. And so let me summarize what I said. Okay, number one, entanglement spectra and entanglement Hamiltonian play this paradigmatic role at the interface of entanglement theory and many-body physics. I think that's really true. And there's a lot of open problems there. Nobody has ever really seriously measured these things except our quench dynamics, but this was maybe more heuristic. I would like to see Bisognano-Wichmann and conformal field theories to be tested. And as I said, we have the tools for that. So we have developed this kind of what I call the EHT recipe with this local Hamiltonian. I really want to emphasize we can fit, we can verify, we can improve, but the whole thing is systematic. And if at the end a local Hamiltonian is not true, it will tell you, okay? It will tell you. So it's not that you fit and then you go home. No, you verify, okay? So it will tell you if it's true or not. So applications go from heuristic, what I showed, to then deep foundations, and it provides experimental observables like von Neumann entropies that we can now measure with these techniques that were not measurable before. And all of these things work at various platforms. And well, I had to include here this slide that shows you 20 ion data where we can also do that with 7. I don't want to talk about it because then there's so much mess down here. We got so many entanglement spectra here that they get it kind of hard to see. Last comment I would like to make, very brief, is this. What we have done in our approach is this, that we have talked about EHT protocols, and we have doing essentially quantum state tomography. And we made quantum state tomography efficient, scalable, by making a claim and making statements about the quantum states that are generated in quantum simulation, namely, which at the end it simply means that our entanglement Hamiltonians are local and few body. And Bisognano-Wichmann conformal field theory tells you that's true, but they are very special corners, and there may be a much broader region. In particular, go to two-dimensional systems. We can apply these ideas to two-dimensional systems right away, where theorists are not able to do calculation. What's the limitation right now? Well, our limitation is not the efficiency of the tomography. We need very few measurements, but our classical post-processing to get the entanglement spectrum out at the moment requires us to store these density matrices, for these subregions on our classical computer. So this means that our analysis right now, not the quantum measurement, limits us to system sizes of maybe 12, 14 particles. I talk about the subregion. The total system can be much, much larger. Talk about the subregion. So you might ask, can we do better than that? Are there quantum algorithms where we can maybe have a quantum advantage, where we don't need this classical storage to represent our entanglement Hamiltonian, where we do this processing non-classically? And the answer is, yeah, we are working on some of these ideas. I wanted to include a few slides along these lines originally, but I didn't really have time now here. But we are just basically gearing up to write a paper with Bhuvanesh Sundar. Christian Kokail provided some results in this context where we can do that also for Hubbard models. So the statement is, a quantum gas microscope is able in these quantum algorithms to provide you with data that allow you to test things like Bisognano-Wichmann, even in higher spatial dimensions where the conformal field theory and all of these things are not really valid. So that's sort of my take on all of that. I hope that I convinced you that what we do is practical. It has a practical application aspect that we can explain and analyze experiments as they exist today in the lab. Talking about quench dynamics, ground states, so on. But I think the real statement is that I'm intrigued that in this quantum simulation, we are opening some new frontiers where we start to talk about, seeing entanglement and this, entanglement Hamiltonians in ground states. Is Bisognano-Wichmann valid or not? Learning something from the corrections, or at the end, and even developing new kind of algorithms that go beyond what we did actually the talk here today. So with this, I would like to thank you for listening, and sort of sorry for going over time. There were questions in between, so maybe this counts a little bit. Yeah.
All right, well, since it's a Zoom talk, I will give you the single person applause.
Peter, it's Charles. This idea that entanglement can be changed significantly by a quench in a non-trivial way is quite fascinating. I mean, what sort of bounds are there on it? Is it possible to take for a quench to eliminate entanglement or to cause entanglement of a state that was previously was not?
So normally the kind of experiments that we have in mind is really we are asking the question, how does a system thermalize? Initially you got a product state that the experimentalist prepares. So this means that the reduced density matrix is just rank 1. It's just the product state. But we know that for a very, very long time, you get a Gibbs ensemble out. I mean, that's what you learned in quantum statistical mechanics, and you happily calculated and partition sum and all of these things that you ever did there was based on this assumption. This state at the end has actually normally volume law entanglement. If you got finite temperature, you got volume law entanglement. So this quench dynamics, this thermalization reveals how we go from a product state to something at the end where the subsystem becomes a Gibbs ensemble and has volume law entanglement. And this whole time evolution, from this trivial product state to this volume law entanglement, Gibbs ensemble in the long run, this is sort of what this thing is trying to investigate. Of course, from an experimental point of view, let me add, there is no closed system, and so you might ask the question, what's the role of decoherence in what we do over here? We have to make decoherence models for some of these things. And of course, these experimental data that I talked about, they only go up to a certain time. And if you ask, in the experimental data that I show, do we see thermalization? I can only say at the point where the experimentalist stopped to take data because decoherence got so large, you're not in thermal equilibrium yet. I mean, maybe the von Neumann entropy has reached a certain plateau, but if you look at the whole thing closer, you're not in thermal equilibrium yet. So the whole thing from product states to volume law entanglement, given the experimental constraints of finite coherence time, this is sort of what could be answered in this quench dynamics. And if you ask, can the whole thing also purify? Well, we can do the same thing also with open system quantum simulators, where you couple to an environment, and we can do a very similar analysis. If you ask me what's the entanglement Hamiltonian in an open quantum system, the answer is honestly that I don't really know, but I do know that I can make open system quantum simulators that purify, that go to complicated pure entangled states, and our machinery would be able to somehow measure that. Okay, but open quantum systems, I think, is kind of an open quantum problem in this case, and this intuition of what the entanglement Hamiltonians are, that definitely exist, and the deeper relation to decoherence and this openness to the quantum reservoirs. All of these things are a completely open theoretical question, but clearly one can do experiments along these lines, and the machinery, I think, should follow these lines and what we're doing, what we're actually doing here.
Thank you.
So this is Bill. You emphasized a number of times that one of the keys to making this whole business work is the fact that the Hamiltonians are local or quasi-local. So I presume that if you had, for example, an all-to-all interaction, that this would fail to be an efficient way of getting things. But what I'm wondering is, how fast does it fail? In other words, if you start to ask for Hamiltonians that are, not next nearest neighbor, but next nearest neighbor, how fast does this thing fail? Or am I even asking the right kind of question?
No, I think that you are asking the right kind of question. The discussion that we had earlier with the quench dynamics, I would say, was actually an example of this type. What the experimentalists realized in the quantum simulator with trapped ions is, of course, a model having long-range interactions. And it turned out that the reason, sort of, not very intuitive in terms of the Hamiltonians that we produced. We talked about all of these corrections to the deformation, of the system Hamiltonian. And part of the reason why these corrections happened was that our region that we had, that we could look at, say 5 out of 10 or 7 out of 20, was relative to the range of the interaction somehow too small for many of these things like this quasi-local Hamiltonian to apply. So the ion experiment was to some extent an example for what you point out, namely that there was a long-range interaction and the whole thing shouldn't really work so well, but nonetheless, with a few extra terms, we were able to fit it. So one of my conclusions from this whole thing is that, actually the whole thing works much better than it's supposed to do. Maybe there's a deeper reason behind it, that it works so much better than we expected to do. like also if I talk about conformal field theory, this is supposed to work only for a quench to the critical point of a phase transition. This is where conformal field theory tells you, is able to make a prediction. If we go away from that, we find that it is actually amazingly still valid. You know, we have now the tools to find out if there's additional terms that an experiment might detect. But theorists, if you go to higher dimensions, 2D or 3D quantum simulators, nobody is able to calculate these things. So there's the potential for discovery that maybe some of these corrections, you go away from these formally exactly solvable points to a broader region. We see that it's still sort of valid to detect some maybe new physics. So my statement is simply it works much better than it's supposed to be, and maybe there's a deeper reason behind it. But this would also require us maybe to go to regimes that are outside where we as theorists understand it, like going to 2 dimensions, for example. But that's,
So,
I think your question was right at the point.
So do you have examples of where it does fail, or is it always working pretty well?
Well, I can give you a trivial example where our entanglement Hamiltonian tomography fails, but the example is sort of trivial in the following sense. Imagine that the state that I'm evolving to is an infinite temperature state, you know. Then my reduced density matrix is just the one operator. All of the entanglement spectra, and we got, 2 to the power n, eigenvalues, they're all degenerate. If I try to fit to an infinite temperature state, in my case, if I try to fit to an infinite temperature state, my entanglement Hamiltonian tomography, I will fail at infinite temperature because, the Hamiltonian is 0, but basically, you can put in whatever you want. So this is an example where these things fail. There's other examples, if I go to the ground state, I talked about Bisognano-Wichmann, and Bisognano-Wichmann was assuming Lorentz invariance. So the quasi-particles are propagating, by the dispersion relation, which is Lorentz invariance. If I take a quadratic, like I take fermions in 2D, so quadratic Hamiltonians, Bisognano-Wichmann is also supposed to fail, as one example. Nonetheless, it somehow works pretty well, So I'm only saying that these things sort of seem to work much better than they are supposed to. And we know some examples where these things fail, but maybe not as drastically. And so right now, what we're doing, for example, is that there's these SSH models that one can do with Rydberg simulators. We can apply to these topological phases, really see Lee Haldane in this context. And so this would be one of the examples, but then also going outside. So trying to see all of these ideas fail by itself, I think would be a very interesting enterprise by itself.